All right, hello, I'm Kunal,
I'm Samya.
I'm Falak.
and this is our GPU programming project demonstration, video demonstration. So I'm going to quickly summarize what the project is. This is basically a CUDA accelerated ray tracer. It basically takes object files, loads them, and renders it into 3D visuals, and it has realistic lighting effects like primary rays, reflections, shadows, and we did this using Labertian reflection models for the lighting calculations. And our application also will have a movable camera system to um, visualize the rendered display from various angles. So we're gonna demo that now. Samyak, take it away.
All right, so in order to run this, first you clone the repo, obviously. Then you can run our install script, source install.sh. It'll take some time to run, so we're probably going to speed this up in post. All right, so our install script is done. Before we move on, I want to mention that in the install script, we export a display variable. This has to match your X11 server that you can SSH with. Otherwise, the window GUI from our program will not render on your end. For more information, you can always read the README for that. Either way, once you're all set, you can to add an object, you can add the object right here. So for example, I want to render the scene object, so I'm going to add it to the run script, and then I will run it. It'll take some time to compile because this is a rather large file, so I'll probably fast forward this in post. And you can see our scene. It is very, very laggy, so it does take some time to rotate or move it around.
The red object, by the way, is the sun, so that's like a reference point just for lighting, just so it's easier to visualize.
And you can see here that we have shadows of the tree on the backdrop, as well as the entire backdrop itself having various lightings based on the light. Let me try zooming in a bit. And yeah, this is our project.
Yeah, and we have other objects that we did for testing that you can see in our project report. Those include a Bugatti, a simple tree object, and a very basic shapes object, like a small triangle. And what we noticed is the larger the file was. Now, for the file loading process itself, we actually used a tiny object loader from a GitHub repository, and we utilized that for object loading for our project. And the bigger the file was, the more annoying it was the more slow, the more laggy it was to render for the ray tracer was more laggy. So, for example, in a shape.object, we had a total of 8 triangles, and the FPS was 39, and our render time was only 22 milliseconds, and very little input lag. And then with tree.object, it was the second smallest file, 13,000, about 13,000 triangles. FPS was dropped to 5, and we had a render time of 187 milliseconds around. A small input lag, but it's manageable. And then scene.object had about 800,000 triangles and FPS of 0.13. So it's dropped drastically. It's basically zero. It's basically zero by that point, and there's a lot of input lag. So render time was about like 7,000 to 9,000 milliseconds, depending on like which could vary. Yeah, and then the Bugatti was such a large file, like about 74,000 kilobytes, I think. That so many triangles, it was 1 million, more than a million, I think, and FPS was barely above zero, like 0.1 again, and it doesn't even render the whole object fully. So that's kind of how this ray tracer works. It works better the smaller the file size is.
And for some of the challenges that we faced on this project, it took a lot of time to get used to STL. as the installation and X11 server setup took a long time, as well as learning the syntax, as it was a very new software for us. The coloring was also in the RGBA format, but with hex, which was not anything that we hadn't seen before, but it was definitely something to get used to and adapt to. For ray tracing, it was very difficult balancing between GPU memory usage and performance, especially for very large complex object models with a lot of polygons. Ray tracing implementation itself took a while because it requires vector complexity, which we were not used to. We had to change the way we thought about our 3D visualizations in order to understand how ray tracing could actually be applied. In that process, we also came across problems with light source position. We tried implementing the Blinn-Phong algorithm, but it was more complicated than Lombardian, as it required messing with the camera settings. Due to our limited time constraints for working on this project, we decided to go with the simpler Lombardian algorithm and put Blinn-Phong aside for now.
Okay, with that, I think that concludes our video presentation. We hope you enjoyed, and if you have any more questions, feel free to shoot us an email or ask. Anything else you guys want to add?
Yeah, make sure to like and subscribe too.
Yeah, thanks.
I want to emphasize the camera part, especially the camera with relation to the model and the light source. Balancing the positions and the rotations and what we should versus should not change or keep constant was definitely one of the biggest challenges that we had. And yeah, I'm proud of our output that we have so far, especially given our time constraints and our knowledge going in as well.
Yeah, I feel like I've leveled up as a CUDA developer for this, and I've actually become passionate about graphics programming now. So yeah, thank you for listening, and yeah, let us know if you have any questions, and hope you enjoyed our project.